Hi, everybody. Welcome to PAW. Today we have Ambar Sengupta from University of Connecticut, who's going to talk on Laplacians and polynomials on spheres, the large and limit. Ambar.
Oh, thank you very much, Irina. Thank you for the invitation. So I would like to speak about spheres in high dimensions and the behavior of the Laplacian as well as polynomials on these spheres. Now, when I say the sphere, it might seem like I'm speaking about the unit sphere, but in fact, the spheres we are concerned with are expanding with dimensions. So it's in n dimensions, we'll look at the sphere of radius square root of n. I'll also discuss some purely algebraic aspects of classical polynomials like spherical harmonics on these spheres. So here's a picture of a sphere in 3 dimensions, but in n dimensions, so with radius square root of n. I guess I'm kind of proud of this picture, which I probably stole from somewhere and then modified or something like that. So the thing is that we'll be working with a surface area measure of normalized to unit mass. And in the kind of objective, one of the goals is to understand why the uniform measure of total mass 1 on this sphere goes to Gaussian measure in infinite dimensions as n goes to infinity. So that's again the statement: as n goes to infinity, the surface area measure goes to Gaussian measure. So a little bit of history. One of the early versions of this result was in a paper of Boltzmann in the context of physics, for he was studying the motion of molecules in a gas. And there was also Maxwell, who was studying the same kind of problems around the same time. Now, I looked at both their works, and it seems Boltzmann's approach is closer to what we will be describing. And also, I noticed that, Euler's integration e to the minus x square dx from 0 to infinity, in his approach to that computation, there are elements of this kind of thinking. Do something for n and let n go to infinity. Okay, so let's look at a little bit of the physics background. We think of a box containing some gas with n molecules, each molecule having mass m, and we have these velocities v1, v2, vn of the various gas molecules. Then the total kinetic energy of this gas is this sum, half mv1 square and so on, half mvn square. You add them up. Each one is the kinetic energy of each molecule. You add them up, you get the total kinetic energy in the gas. And from the theory of statistical mechanics or classical thermodynamics of gases, the average kinetic energy is proportional to what we observe as temperature T. There's a constant K, we ignore that for the moment. So you take the total kinetic energy and divide by the total number of molecules, 1 over n, and what you get is the temperature up to this Boltzmann constant. So if we rearrange this a little bit, we get this equation. And if you look at it from a mathematical viewpoint, all this says is that if you string the vectors v1 through vn into one gigantic vector with 3n components, then that's a point on a sphere whose radius is like square root of n. So that's where the interest in this comes, y square root of n. Well, there you have it. So there I've written, again, that's the point v1 through vn lies on a sphere radius proportional to square root of n. Now, if we just ignore for notational convenience, let's just think of one-dimensional gas, so each of the velocities is just a real number, then the point that we are looking at would be a point in Sn minus 1 of radius square root of n. Again, I dropped the other constant. And if you think that there is no direction that is favored, it's not like there's wind blowing in one direction or gravitation or some other force, then there's no reason why the velocities should be bunched together in any one direction over any other direction. So it's reasonable to assume that at least in some steady state and in equilibrium, the velocities would be distributed in such a way that this point v1 through vn is uniformly distributed on the sphere of radius square root of n. So that is again, that's the reason why one would think of the uniform measure on that sphere. Now, in a typical real gas, the value of n is very large. It's like 10 to the 23 times something, or it may be much larger too. I remember ages ago, the first time I heard a talk with large N something in the title of the talk, somebody in the audience interrupted and said, the case we're interested in is really n equal to 3. Why are you studying large N? And the speaker said, well, 3 is a large number. So in this case, I really do have a large number, 10 to the 23, at least human terms, large. So let's look at a concrete case. Let's take one of the velocities, let's say the first particle v1, and let's just take some function v1 to the 4. Okay? And we take the average value over the sphere. So integral v1 to the 4 over the sphere of radius square root of n, and we use again the normalized measure. And you let n go to infinity, it's a reasonable question, is there a limit even? Okay, so this is the kind of question that Boltzmann and Maxwell were looking at. And their result was that yes, there is in fact a limit, and the limit is this Gaussian integral. And that's what we're looking at here. We'll just sketch the argument in the general case. So again, you take the sphere of radius square root of n in n dimensions. You do the integral of a function you like. I've taken here v1 to the 4. Integrate with the uniform measure on the sphere of total mass 1. Take the limit as n goes to infinity. It turns out to be this Gaussian measure. So more officially, if f is a reasonable function, and it's a function of k coordinates, where k is a fixed number, and you integrate this over the sphere of radius square root of n in n dimensions, and again, the integration is over the normalized unit mass integral. Let n go to infinity, it comes out to be this Gaussian integral. Now, what's the proof of this? Well, if you write out the integral, it's not super complicated, but it works out. I think the conclusion is what is really interesting. There's nothing particularly spectacular in the proof itself. It's more the result that somehow we come up with the Gaussian from a spherical measure. So in a certain sense, one could think of Gaussian measure as probability measure on an infinite sphere. So again, this particular argument is actually there in Boltzmann's paper. Maxwell had some other approach, it seemed to me. Okay, so a question that arises is, okay, so what happens to analysis? You do some analysis on the sphere in n dimensions, so radius square root of n, and you let n go to infinity. Is there are there interesting results that emerge? I don't know, things like isoperimetric inequalities, all kinds of things that one could ask. But in this case, let's focus on the Laplacian, just very basic, interesting operator. So how does it behave as n goes to infinity? So the first thing we need to do is to get a handle on the Laplacian on the sphere. Now, Laplacians on manifolds, all kinds of manifolds, including, of course, the sphere, have been studied, and there's a vast subject of results on the nature of the Laplacian. But in the case of the sphere, we just focus on that one, and we can use an approach that is tailored just to the sphere. This type of question has been investigated by numerous analysts and probabilists and others. Okay, so let's look at the Laplacian and the sphere. So let's start in this way. We start with these differential operators, xj times the partial in the k direction minus xk times the partial in the j direction. This is a differential operator that generates rotations on the jk plane. Okay. So if you are good with that, then that's good. If not, it's just a term. So that's the operator m sub jk. It just operates on the j and k coordinates. Then there's this very nice formula that if you take the Laplacian in n dimensions and you multiply by the norm x square, in other words, x1 square plus x2 square plus xn square, then it turns out to be equal to a radial part and then an angular part. The radial part is the first two terms. And I've written here what r del r is. That's just the sum of the xj del j. I think sometimes called an Euler operator. And then the last term is the sum of these mjk squared. In physics terms, that's angular momentum squared in this high dimension. Another way to view it is to think about it so if you're into Lie algebras, this is a quadratic Casimir of the rotation group. Okay, so that is good. So again, let's see, we have on the left-hand side, the Laplacian in n dimensions, just Rn, okay, with x square. And on the right-hand side, we have the first two terms are differential operators that reflect derivatives in the radial direction. And then the last term is a sum of squares of these things that I call the rotation generators. Now, we'll study a little bit about the behavior, algebraic properties of these operators. If we take the rotation in the jk plane, okay, so I remind you, mjk is this operator, xj del k minus xk del j. So mjk times the sum of the squares, it commutes with that. Okay, this is also, one knows this kind of thing in physics. And similarly, there are other commutation relations. Okay, it commutes with the Laplacian. And these things are useful in understanding the spectrum of an operator. Now, let's look at polynomials. I did say that part of this talk is about polynomials and spheres. So let P sub n be the algebra of all polynomials in n variables. Okay, no sphere, just abstract polynomials in n variables. These operators that we have been discussing, the Laplacian and the angular momentum generators, the rotation generators rather, they all make sense on polynomials. They take polynomials to polynomials. And as we know, a polynomial is harmonic if the Laplacian zeroes it out. So Hn is, we denote by Hn the harmonic polynomials, the kernel of the Laplacian in n variables. So a result, here's a result due to Gauss. If P belongs to Pn, is a homogeneous polynomial of degree d, then we can split it into a harmonic part and another part that is a multiple of x squared. Okay, so again, you take any homogeneous polynomial of degree d, you can write it as a sum of a harmonic polynomial and a polynomial that is a multiple of norm x squared. Norm x squared, recall, is x1 squared plus x2 squared plus xn squared. Okay, and this is a unique homogeneous harmonic polynomial of degree d. And the Q has degree d minus 2. The whole thing has degree d. Okay. So again, this goes back to Gauss, a homogeneous polynomial. You can split it as a sum of a harmonic polynomial and a polynomial of lower degree times the norm of x squared. Now, if we just run this machine repeatedly, you apply that same result of Gauss to Q. Q you can write again as a harmonic polynomial plus again x squared times another homogeneous polynomial, not necessarily harmonic. So if you string this, if you apply this repeatedly, you end up with this kind of decomposition of P. So first of all, there is a harmonic polynomial P0. Then there is norm x squared times a harmonic polynomial P1 plus norm x to the 4 harmonic polynomial P2, and on it goes till you exhaust all the degrees. So that is an interesting decomposition. It's like, expanding a number in powers of 10 or whatever. It's in this case, it seems we can expand things in terms of the powers of the norm x squared. So that is a very useful little, I mean, I shouldn't call it a little fact. It is an interesting fact. Now, notice that if we restrict both sides to the sphere of radius A, on the left, we have the restriction of the polynomial P to the sphere of radius A. On the right-hand side, you see all these norm x squares. They become a square, a to the 4, a to the 2s. Okay, so what do we get? We have this situation here. So this is another way of writing it. Okay, P is equal to P0 plus a square P1 plus dot 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 a to the 2s PS. And then, I wrote it in this way, x squared minus a squared. It doesn't matter. You can see that whatever it is, that extra part, it is 0 on the sphere of radius A. And on this part, the first part, the P0, P1, PS are all harmonic. And so this whole sum is harmonic. So what does this give us? It shows us that every polynomial coincides with some harmonic polynomial on any given sphere. Okay. Again, it's a purely algebraic result, but it's not obvious at first, why should this be? Give me any old polynomial, somehow it's equal to a harmonic polynomial, as long as you restrict it to a sphere. Okay, but there it is, that is due to Gauss. Now this leads us to the following procedure. If we start with the general polynomial of in n variables, so an element of Pn, what we can do is we look at its restriction to the sphere of radius A, and we saw that it agrees with a polynomial, a harmonic polynomial. So that is LA of P. Okay, so here, in fact, we have the formula from before. LA of P is just, again, LA of P is harmonic. P is not necessarily harmonic, but they agree on the sphere of radius A. Notice LAP does depend on the radius A. You change the radius, it's a different harmonic polynomial. One other thing, by the way, there are countless little interesting observations, just purely algebraic. If you have a polynomial that is a polynomial multiple of norm x squared minus a squared, then of course it vanishes on the sphere of radius A, right? But it's also true going the other direction. If a polynomial in x1 through xn evaluates to 0 on the sphere of radius A, then it turns out to be a polynomial multiple of norm x squared minus a squared. Okay. So these are kind of useful little observations. so again, this, if you have two polynomials that agree on the sphere of radius A, then they differ by multiple of x squared minus a squared. That's the part that we are interested in. Okay. Two polynomials that agree on the sphere radius A will differ by multiple of x squared minus a squared. So again, quick look back at commutation relations. It's not quite a look back because now I'm looking at this projection operator. Again, what is LA? LA, you feed it a general homogeneous polynomial and the output is a harmonic polynomial. So LA commutes, actually this is not written correctly, I think. It should be LA here. There's it commutes with the rotation generators, and so if you just apply it repeatedly, you see that it commutes with the norm m square. I remind you, norm m square is the sum of the squares of the operators mjk. Okay, now let's turn to spherical harmonics. So these are functions of great interest in classical analysis. Certainly 19th century, perhaps before, certainly very well studied in the 19th century and even beyond. They're just wonderful objects. These are homogeneous functions that are harmonic. We are only going to be concerned with polynomials. So often one considers spherical harmonics on a fixed sphere. So typically the unit sphere, the idea is, well, look, it's homogeneous, so why bother studying it on other sphere? You fix a sphere, unit radius, and everything else you obtain by scaling. But remember, in our context, the radius, ultimately what we're interested in is in a situation where the radius is square root of n. And so, it changes with the dimension. So we do want to keep track of the radius. So that's what I've said here. The distinction between our study and the classical theory is that in our case, both the dimension and the radius of the sphere are important and need to be tracked. So we don't restrict to the unit sphere. Okay, so let's recall this magic formula. Norm x squared times the Laplacian is the sum of three terms. The first two terms are sort of radial differential operators, and the last term is this sum of the squares of the rotation generators. Okay. And we may recognize these things. I mean, you may know it in n dimensions anyway, but in 3 dimensions, certainly it's dealt with in calculus. Okay, so now let's see what happens as big N, the dimension of the ambient space varies. Now let's fix a polynomial in small n variables, small n being less than big N, and everything's happening in this larger dimensional space, the larger dimension being big N. But we are considering only polynomials of the first little n variables. Now, if we look at this norm m square, that operator that keeps appearing on P, in principle, this, m square it's not restricted to just the first little n variables. It's everything, it involves everything from x1 through x big N. So m square P is a polynomial in all the variables. But it turns out that in fact, if you again restrict to the sphere of whatever radius A, then there is a unique polynomial depending on A in the variables, just the first n variables. Okay. So there are other things that it coincides with that on that sphere. So now let's do this. We're going to define. So again, look, the Laplacian on a sphere you can define in any number of ways, but I'm proceeding in a way that is purely algebraic. Okay, there's no analysis involved. for now. So we define it as follows. You apply the angular momentum squared. I keep calling it angular momentum. That's the physics language. So the sum of the rotation generator squareds applied to P, and then we scale it down by a square. Okay? So again, this is a polynomial in all big N variables. However, when we restrict to the sphere of radius A, we can choose a polynomial in the small n variables that coincides with Q. And so that is what we will take for the Laplacian. Now, actually, it's better to just work out an example. So let's just work out this spherical Laplacian of x1 to the m. Okay, this, I mean, if we are to understand the Laplacian, we better be able to work this out. Okay, so x1 to the m, and we apply the norm m squared. So remember that sum of the mjk square x to the x1 to the m. mjk, if you go back all the way, you'll see that it's xj del k minus xk del j. Now, here we only have x1. So any partial derivatives other than in the x1 variable disappear. So it's quite easy to calculate. If you work this out, you get what is in the first line here. Okay. Again, it is a completely straightforward calculation, nothing tricky in there. Now, remember, we are focusing on the sphere of radius A, so anything that vanishes on that sphere, we mod it out. So we might as well put a square in place of norm x square. And look, we have a polynomial then. You see the first polynomial here involves norm x square. So it involves all the variables x1 through x big N. But once we put norm x square equal to a square, it just becomes a polynomial in x1. Of course, it has an a in it, but it just involves x1. Okay, so then our rule was, or definition was, that we should divide that by a square. So let's take this and divide by a square, and that's what we get. Okay, that's the Laplacian of x1 to the m. Now let's look quickly at the case of the sphere radius square root of n. This means we take a squared to be n. If you plug in a squared equal to n in this formula, you get this. And at first you can say, well, okay, fine, but so what? But there is something interesting to note here. Look, its dependence on big N involves 1 over big N. Again, we computed a Laplacian, and its value turns out to be dependent only on 1 over big N in terms of its dependence on big N. So what's the significance of that? It means that we can actually let big N go to infinity and get something, a reasonable limit, right? So again, I've written the Laplacian of x1 to the m. Okay, the spherical Laplacian as we have defined it, and then you let big N go to infinity. Well, I haven't done the limit here, it seems, but anyway, want to point it out. Okay, now let's look at the L2 space on the sphere of radius A. So we have the inner product of P and Q, two polynomials is PQ bar. Here, sigma is the normalized measure on the unit sphere. So this gives an inner product, except that those polynomials that vanish on the sphere will, of course, have inner product 0 with anything. Okay? So modulo that space, we are good. Okay, so now we go back to our Sn minus 1 square root of n. Okay, let's see what happens here now. So the inner product we're working on is, let's go back a bit. the inner product I have indexed by A and N. Okay, A is the radius, N is the dimension. So here, the radius is square root of N, the dimension is N. Now, from the Maxwell-Boltzmann law, we know that if, after all, this inner product is actually the integral over the sphere with the uniform measure of total mass 1. And the limit, as we saw by the Maxwell-Boltzmann law, is the Gaussian integral. So the limit of the L2 inner product on the sphere of radius square root of N turns out to be the L2 inner product of the polynomials with respect to Gaussian measure. Okay. Now these are polynomials in finitely many variables, so nothing super fancy going on here. Okay, now let's go back to our rotation generators. Xj del k minus xk del j, that's mjk. It's a reasonable question, what kind of operator is this on that L2 space? So if you work through the integrals and all that, you'll see that mjk is Q adjoint, and this agrees with the physics intuition that rotation generators are skew adjoint. Then the sum of the squares of mjk's, that one is Hermitian with respect to the inner product. Then the harmonic projection LA, so I'm just, these things just have to be computed, and it turns out that this is also Hermitian. So that's actually an orthogonal projection, this LA. The spherical Laplacian itself is Hermitian with respect to the inner product on polynomials. So I'm not saying going into self-adjointness, which one can do, but in this case, one could say this is basically an algebraic result. If you do the inner product of P with Laplacian of Q, then it's the same as Laplacian of P with inner product with Q. So all of these follow from, again, algebraic manipulation of these operators mjk. Okay, so finally we come to, in the title of the talk I said large n behavior of the Laplacian. So here it is. Let's take the polynomial P in some fixed number of variables n, focus on the sphere, take the spherical Laplacian, let n go to infinity. Well, it turns out that it has a limit. We already saw for x1 to the m, it has a limit, right? So this is true in general for a polynomial. It turns out this is a certain differential operator applied to P. And what is that differential operator? Well, here it is, script H. So this is a key result. Okay, so again, stepping back, you think of a polynomial, let's just say in 3 variables. You view it as a function of x1, x2, x3 on a sphere of humongous dimension, or radius square root of n. Take the Laplacian, let n go to infinity. Is there a limit? The answer is yes, there's a limit. And in fact, that limit can be obtained by this kind of differential operator applied to P. It's Ornstein-Uhlenbeck. Okay, so going back to x1 to the m, we had derived this formula. We had computed the Laplacian and we found it to be this. So if, this is a remark I had already made before, if you let big N go to infinity, you let the dimension blow up, then you actually get a nice formula here. And if you look at this, look what this is. This is actually the same as, well, it should be infinity here, but Of course, you know, all the other terms in the differential operator don't matter because we are only having a function of x1. So the second derivative of x1 to the m is m times x1, m times m minus 1, x1 to the m minus 2. That appears as the second term in the limit of the Laplacian, and then the first term in the limit of the Laplacian arises from this Eulerian term, xj delta xj. So we've actually proved the result for the special case of the function x1 to the m. Next, let's look at a product of two polynomials, p and q. So by working through various steps, you can show that there's a peculiar behavior. Look, it's almost like a first order differential operators. If p and q are polynomials in different sets of variables, and you take the Laplacian of the product of p and q, and you let n go to infinity, there's some kind of a Leibniz rule, like product rule that's taking place. And that's actually key, because look, if we know how to take the limit of a product and we know how to take the limit of a monomial like x1 to the m, then we can just take limits of any polynomial, right? Any polynomial is a sum of monomials. Each monomial is a product of powers of x1, x2, and so on. So that is that, and that is the outline of the proof of this result. Okay, we're close to done. Now, spherical harmonic, there's a related concept which is called a zonal harmonic. Basically, it just is a spherical harmonic that is a function of one variable. Now, you could insist, well, that's a variable, that's a general variable, maybe it's some combination of x1, x3, x18. But let's just say it's a function of x1. So it's a spherical harmonic whose restriction to the sphere is a function of x1. Then if you take the harmonic equation, so Laplacian of the polynomial is 0, and you write the polynomial as polynomial in x1 plus something that is 0 in the sphere, and work out all the steps, you'll see that a zonal harmonic, when viewed as a polynomial in x1, satisfies this ordinary differential equation. And these monic solutions are called the classical Gegenbauer polynomials. So again, this is in fixed n dimension. So one might ask what happens when big N goes to infinity. Well, by methods, if you put everything together, what we've been discussing, it turns out that this Gegenbauer polynomial in the large N limit becomes a Hermite polynomial. Okay, so we're almost done. I think we're done. Okay, so where are these results from? So first of all, I need to say, look, it's very difficult to do anything new with spherical harmonics. There's been, people have spent hundreds of years studying them, but one can, have some new insights and new approach. So that's what we have done. And a lot of the work I've done, frankly, has been grown over the years in working mostly with my former PhD students. And this particular discussion relies on this paper, Polynomials and High-Dimensional Spheres, and a work I did with my colleague, Keith Conrad, that's on the purely algebraic side. If anybody watching this or listening to this is interested in spherical harmonics, all I can say is a beautiful subject, and you never know, maybe there are more things to discover. All right, well, thank you.
Thank you, Ambar. Are there any questions? Let me ask the obvious question. connection with the radon transform and polynomials. Could there be hyperplanes generated by these polynomials?
Yes, so there are certainly questions there that are of interest, at least to those of us who are interested in the radon transform. Well, for instance, you take a polynomial, you integrate out over some kind of a circle on this sphere, and you look at large n limit. Do you get a Gaussian radon transform? I mean, surely you do, but some formulations have been proved in some form in the literature, but I think in the context of polynomials, it would be particularly interesting to explore.
Mm-hmm. So this hasn't been done.
Yeah. No. Also, I don't know anything well, I mean, maybe I'm imposing the question myself sometimes. One wonders if instead of the Laplacian, you have some other differential operator.
Yeah. Interesting. Other questions? Okay, so then thank you so much, Ambar. Here's some virtual applause.
All right. Thank you so much. Thank you all for here, and thank you all who might listen someday somewhere. Thank you very much.